What's up, everyone? Thanks for watching another episode. Today I'm going to cover the long-awaited example. Now this is a nice little example that's going to touch on all of the previous videos that I've discussed, and it's going to bring us to the conclusion of our spring mass analysis. Next video I'm going to introduce damping, which makes it more interesting, and we're going to learn some new neat little tricks for analyzing systems. So pause this video and give this example a go. It's similar to the comparison I did in the previous video for initial conditions, but pause it, give it a go, and see what you get. All right, so let's go through this step by step. You can see that we've already been given the general solution. We don't need to derive this every time we use it. So it's a good one to remember. So what we're going to do is I'm just going to jump straight in and find our omega n, because that's the first thing they've asked us to find. So we know that the equation for omega n is equal to K on M. So in this case, we can see that our K here is 8 Newton meters and mass here is 2 kilograms. So we just plug straight in. We get 8 on 2 square root, which is equal to the square root of 4, which is equal to 2. Now, you might be wondering, well, what are our units here? And our units are rads per second. We'll just do a quick unit balance to make sure that these units are correct. And this is a great thing to be able to do because it's important to be able to check your units. So we have newtons on meters divided by kilograms, all square rooted, which is just going to be equal to newtons on meters times kilograms square root. Now everyone should know what the SI units are for newtons. So we have, or the breakdown SI units. So we have mass times acceleration. So it's going to be kilograms times meters per second squared divided by meters times kilograms. And this is all square rooted. So you see the meters cancel with the meters, the kilograms cancel with the kilograms, and all we are left with is 1 on root seconds squared, which is equal to 1 on s. Now, because we're using the format for the sine and cosine of omega nt rather than something like cosine 2 pi omega t, this 2 pi would convert this to radians if this was in hertz, but because we're not using that, we're using radians already. So this is radians. If you get confused by it, just do a little Google of it and it'll basically explain the difference between radians and hertz. So basically, omega n in this format is always in radians per second, and typically we use radians per second because it's a lot easier. So there we have it. We have our omega n. Our natural frequency is 2 radians per second. So there's the first part of the question done. So the second part is determine A and determine B, which are our constants up here that we talked about last video. So the first thing we'll do is we'll just plug our initial condition in. Now I stated before, but this little subscript might still confuse some people, but x of 0 is equal to, it's equivalent to x of 0. So this is important because that's what we're doing. We're taking time is equal to 0. So for this example, this is equal to 0.001, which is, I'll just keep going, which is equal to, we substitute 0 into our general solution and see what we get. So we have A sine times, I'm just going to substitute 0 in because 0 times omega n is still 0. We have 0 plus B cosine 0. So we can see that sine of 0 goes to 0 and cos of 0 goes to 1. So then what we have here is we can see that B is equal to 0.001 0.001, and we're given this in meters, 0.001 meters. So there we have B. So that's our first constant found. Now, we should differentiate this. I'm sure you know that this is going to give our A term 0 from our last videos, but we'll go through the motions anyway. X dot of t is equal to negative A cosine omega n t times omega n plus B sine omega n t times omega n. So now we just substitute in time is equal to 0 because this is our initial condition. X dot of 0 is equal to, so we have minus A, let's bring omega n over here, cosine of 0 plus B sine of 0 times omega n. So we can see that the sine of 0 is going to be equal to 0 and the cosine is equal to 1. So what we get is this is all equal to 0 from this equation up here. So we get minus A omega n equal to 0, which just gives us A equal to 0. There we have it. We found our two unknown constants and our omega n. So now we can substitute everything back into our general solution, our constant A, B, and omega n, and find the final solution for the system. So the displacement at any time t for this system is equal to, our A term is 0, so we'll ignore that. So we plug it in our B term, which is 0.001 times cosine omega n, which is equal to 2t. Now this is given to us in meters, and our velocity is also in meters per second. So everything's in SI units, so we also have meters here. And there you have it. For any time t, we can find our displacement of this spring mass system. All right, guys, so I hope this helped. Please like and subscribe so I can bring you more videos. Next video, we're going to be talking about damping. So we're going to introduce some new terms and concepts. I'm not going to go through any more examples on spring mass systems because when we start damping, we're going to be still using all of this information. So you're going to get lots of practice with doing everything we've learned in the spring mass system analysis. So I hope this helped, and I'll see you in the next video.